the determination of microplastics in complex matrices like biological samples, where the impact of unwanted matrix interferences shouldn't be underestimated. And in particular, I will show you an example of determination of microplastics in fish meal. So we know that many different analytical approaches are available to gather information on microplastics. Information like particle numbers, size, area distribution, identity of the polymers and additives, mass fractions, and the state of degradation. But while there is no comprehensive method to get all such information, different techniques can be used to piece together the whole picture, and each technique, of course, has a limit and advantages. Microscopy is very useful for assessing morphological and physical classification. It is typically combined with spectroscopic techniques like FTIR and Raman. And with those techniques, the level of microplastic contamination
sorry.
Yes?
Your voice is not clear. Maybe can you use the microphone closer to you? So it's okay now, but when you speak during the presentation, somehow it is breaking. So can you keep the microphone closer to you?
Yeah, I can try.
Now it's better, but when you are doing the presentation, it was not good.
Oh,
so please,
okay.
Please continue. Thank you. Sorry for the interruption.
Okay, no problem. Hope you can hear me well now. So I was saying that those techniques, microscopy and spectroscopic techniques, can assess the level of microplastic contamination based on particle-related information like particle numbers or through imaging approaches. Typically, those techniques allow the determination of microplastic down to a size of about 10 micrometers for FTIR and about less, down to 1 micrometer with the Raman. However, in order to retrieve mass-related information, it is necessary to apply thermoanalytical methods where the sample is thermally heated or decomposed, and then it is analyzed for identification and quantitation for the extracted compounds or the decomposition products. Thermal analysis include TGA, thermogravimetric analysis, thermal desorption, pyrolysis, thermo-extraction desorption, and all of those can be combined with the GCMS for mass quantitative and qualitative information. The detection through the GCMS allows to identify and quantify the amount of microplastic through the characteristic thermal degradation products and their respective indicator ions. One benefit of the thermoanalytical methods is the capability to detect bulk amounts of micro and nanoplastics much below the lower size limit of microscopy and spectroscopy techniques, offering a very low detection limits in the range of picograms to micrograms. So plastic pollution in the marine environment is of particular concern because it impacts the entire marine life food chain. Most plastics have a very long degradation time in the order of centuries, and this material degrades in size over time, ending up to micro and nanoplastic through weathering. Due to their characteristics and due to the additional content of pollutants like plasticides, flame retardants, and other organic contaminants, micro and nanoplastic have a complex toxicological effects on marine life. Due to their small size, micro and nanoplastic easily enter the basis of natural food chains, mainly through direct ingestion. This is, of course, representing a risk for the aquatic ecosystems and also for human exposure through consumption. The scale of global microplastic contamination is only starting to become clear, and in this interested paper that I'm referencing here, there is a demonstration that plastic nanoparticles are toxic and reduce the survival of aquatic zooplankton. Fish feeding the plankton containing plastic nanoparticles change their behavior. The nanoparticles can actually penetrate the brain barrier in fish, causing behavioral disorders. The paper demonstrates how plastic nanoparticles are transported up the food chain, such to be detected in brain tissue of the fish. And since this is an emerging field, there are limited studies so far on the identification of plastic polymers, and stringent quantification requirements remain to be developed. As mentioned in this presentation, I'm going to show the potential of accurate mass detection for the characterization of plastics and the quantitative performance which can be achieved. In this study, we used the thermal degradation of samples through pyrolysis coupled to high-resolution accurate mass spectrometry for the qualitative and quantitative analysis of microplastics. A multi-shot pyrolyzer from Frontier Lab was connected to the Orbitrap GC-MS system. The high-resolution MS detection offers enhanced selectivity that facilitates the detection and quantification of low level of compounds against a complex chemical background. In this slide, you can see the conditions used for the characterization of plastic polymers, as well as for the quantitative determination in fish meal samples. The Orbitrap acquisition was performed in full scan mode from 50 to 650 mu. And in this way, the method setup is really very easy at a resolution of 60,000 for the Orbitrap. This study was conducted on the Orbitrap Exactive GC-MS system, as shown in the picture. However, I'd like to mention that early this year, a new model of the Orbitrap GC-MS has been released to the market. This is named Orbitrap Exploris GC. It is much more compact, as you can see from the image, while providing extended resolution capabilities up to 240,000. This slide is representing the inner view of the Orbitrap Exploris GC240. The sample components coming from the GC enter the Extractabright ion source. The system comes with two sources which can be configured for electron impact or chemical ionization. The Extractabright is a wireless ion source, and thanks to the vacuum probe interlock, it can be easily and quickly removed for replacement or maintenance without venting the system. This design allows as well for column exchange without venting the MS. Then there is an S-shaped ion guide preventing neutrals to enter the quadrupole, and this is reducing the noise and is also increasing the robustness of the system. The ions can then enter the AQT quadrupole, which is responsible for mass isolation for the selected ion monitor acquisition or for MS-MS acquisitions. It allows for mass isolation down to 0.4 Dalton for improved selectivity, but in the same time, it is assuring high ion transmission for high sensitivity. So towards the end of the ion path, we have the core of the system, that is the C-trap for collecting the ions before the introduction into the Orbitrap mass analyzer. Ions from the C-trap can also be sent to the HCD cell for MS-MS fragmentation before recollecting and send them to the mass analyzer. So C-trap and the Orbitrap mass analyzer, as mentioned, the core part of the system. And I'd like to spend a few words to explain how it works and how the Orbitrap mass analyzer can separate ions with such high resolution. As you can see from the drawing, ions are stored and cooled down in the C-trap. And then, thanks to a push-pull lens system, the ions are ejected and accelerated along lines converging to the Orbitrap entrance. As the ions enter the Orbitrap, they are squeezed towards the inner electrodes by its electrical field and start rotating around it. Additionally, the bell-shaped outer electrodes induce an actual oscillation which frequency depends only on the ion mass to charge ratio. And therefore, such oscillation frequencies are used for the ion mass determination. Worth it to note that the signal is due to the current generated by the oscillating ions, and it is measured at the outer split electrodes. So there is no electromultiplier in the system, so there is no more need for electromultiplier replacement. Of course, there are many ions in the orbit trap, and those are generating a very complex signal. But the frequencies are actually determined using a Fourier transformation. The mass's resolution increases with the number of oscillations. So more oscillations and more focusing of the ion with the same mass to charge ratio is achieved. Since the smaller masses are oscillating faster than heavier masses, the resolution increases for the smaller masses, and this is making the orbit trap particularly suitable for GC application when high resolution MS is required. The applicability of the Orbitrap GC-MS in combination with pyrolysis for the qualitative and quantitative assessment was tested using both standards, plastic standards, commercial plastic standards, and fish meal samples, which has been spiked with a known amount of plastic polymers. Between 0.3 and 0.5 grams of fish meal resulted in about 5 to 10 milligrams of decomposed material, which was spiked with 2.5 microgram of polymethyl methacrylates and 2.7 gram of polystyrene in the ethyl acetate standard solution. To evaluate the identification capability of the system, we used solid polymer samples as listed in the slide. As a single polymer sample, and as well as a mixture of all the polymers with 10 to 100 microgram for each polymer in the mixture. To all sample, 10 microliters of tetramethylammonium hydroxide was added as a methylated agent before analysis in order to protect polar compounds released from the pyrolysis experiments. As I mentioned, the acquisition has been done in full scan. And here you can see the extracted ion chromatograms for styrene and methyl methacrylate, which are used to assess the response linearity. Linearity was tested using polymer standard at a concentration ranging from 0.05 to 50 microgram, which is the range that corresponds to the amount found in real samples analyzed with the pyrolysis GC-MS. On the left-hand side of the slide, you can see the number of scans per peak exceeding 20 scans for a 3.5-second wide peak, allowing for an accurate peak integration and compound quantification. Excellent linearity response were also obtained for both compounds with a correlation coefficient higher than 0.999, and the percentage relative standard deviation of the response factors was below 15%. In addition to the response linearity, mass accuracy of target compounds was verified across all concentrations. Accurate mass information is, in fact, critical to avoid misidentification and erroneous quantification. For all the target compounds, the mass accuracy was less than 1 ppm, irrespective of the matrix complexity or the concentration level. So here is an example of consistent high mass accuracy for all the ions of the mass spectrum for styrene at the lowest and the highest concentration level. In order to assess the accuracy for quantification of microplastic, a fish meal samples was spiked with known amounts of polystyrene and polymethyl methacrylate and quantified back against the calibration plot. Even without using any internal standard correction, the average percentage deviation from the expected results was really very good considering the complexity of the matrix. With the Orbitrap GCMS system operated on a routine base at 60,000 resolution, it is possible to selectively isolate mass values corresponding to the pyrolysis products of various polymers. On the left side of the slide are examples of selectivity for the different polymers, with the typical fragment masses used to identify and quantify the different plastic materials. Ions, which goes from a mass to charge ratio of 78 for the PVC to 228 for polycarbonates. The minimum mass window, which is meaningful to use when extracting the quantifier ions, is a function of the used MS resolution. For those polymers, the ions are extracted at ±5 ppm, which is just above the smallest mass difference that can be resolved with a resolution of 60,000. The many characteristic peaks of the pyrolytic products are clearly visible for those polymer types with small monomer like the polypropylene and the polyethylene. Another important feature is the clear multimers pattern for the polystyrene, which is necessary for the selective quantification of this polymer when we are excluding the monomeric styrene. In this case, in fact, styrene monomer needs to be excluded from the quantification, since it is a pyrolysis product also deriving from the natural marine chitin. In addition, the importance of the high-resolution accurate mass detection in order to improve the selectivity is demonstrated on the right-hand side of this slide for the polyamide fragments, using a much wider extraction window in order to simulate a low-resolution mass spectrometer. As you can see, it is generating a crowded extracted ion chromatograms. When using instead an extraction windows of ±2 ppm and taking advantage of the measured accurate mass, the chromatographic peaks useful for the quantification are actually much more evident. Another example of full scan accurate mass selectivity is shown here for the polystyrene in a mixed sample containing the other 7 different polymers. Accurate mass measurement enables extraction of accurate mass within a windows, in this case of ±5 ppm, as it is shown in the top chromatogram. And this is ensuring confident detection. With the 2 chromatograms below, we could simulate a nominal mass acquisition with an extraction windows respectively of ±100 millimass unit in the center and ±800 millimass unit at the bottom. In both cases, additional interfering compounds, and this is impacting on the identification and on quantitation. Getting high selectivity from the detection system is more important as the matrix become more complex, and maintaining the high selectivity while acquiring data in full scan is really beneficial for many reasons. First of all, the method setup is much easier independently on how many target compounds you may have. And secondly, you preserve a comprehensive analytical information in your data, permitting a retrospective analysis for new target compounds, possibly not considered at the beginning of the study. And the last but not least, a full mass spectra with accurate masses for all the fragments allows for the identification of unknown compounds generated during the pyrolysis process, especially when the spectral deconvolution capabilities of the software can be used. In this study, the Thermoscientific Trace Finder chromatography data system was used on samples on the GC Orbitrap. In addition to the target quantification, Trace Finder allows for untargeted analysis in a routine full-scan high-resolution mode of operation. This approach allows to screen the raw data acquired for the quantitation experiments with the possibility to search additional chemicals resulting from the pyrolysis process. An example is shown here for the alpha-methylstyrene, a well-known degradation product from the polystyrene pyrolysis. In this slide, you can see the Trace Finder deconvolution browser showing the tentative identification of the alpha-methylstyrene based on the NIST library matching with a reverse search index higher than 900. So very good identification matching. And also the fragment rationalization with a confidence score that is higher than 99%. And here you can also see the mass accuracy is less than 1 ppm for the measured fragments from the deconvoluted mass spectrum. So in order to conclude, we can say that sample pyrolysis followed by GCMS analysis is an established available technique for quantitative and qualitative analysis of microplastic in environmental food and biological samples. Especially for complex matrices, Orbitrap GCMS system in combination with pyrolysis is a very promising analytical technique that opens new possibilities for the analysis of microplastic polymers in biological matrices. This technique has been applied to fish meal samples within a study on the impact of microplastic on the marine life. And the high-resolution accurate mass detection is the key to ensure the required selectivity and sensitivity for confident identification of the pyrolysis products from a complex sample. Full scan acquisition with high-resolution accurate mass selectivity is a very powerful tool for retrospective analysis and for the identification of additional compounds produced during the pyrolysis process of the microplastics. Additional information can be found in dedicated application notes, which are available on the Thermo Scientific website, or simply you can contact me if you are interested in having a copy. I will be pleased to send it to you. So before concluding, I'd like to acknowledge the Institute of Marine Research in Bergen for the valuable collaboration, S&H Analytics for the technical support, and the Thermo Fisher Scientific application team for the experimental work. And of course, I thank you very much for your kind attention.